So we're going to talk about finiteness conditions for these classifying spaces for families. So I'm going to start by introducing what they are. I don't know how many people know about these things. I guess a few. So we'll see. And then I say something about a conjecture by Juan-Pineda and Leary about their about the type of those spaces for the family of functions. Family of finite circles, a lot is known. So I'm going to talk about that. So classifying spaces for families. Okay, so, I never forget the co-authors. So this is with Nancy and Petros, yeah. And it's still ongoing. So just G is as usual, the group. And we take F as a family of subgroups of G. So this is what we ask for it to be is closed under subgroups and conjugation. So the family I'm going to mostly talk about today is F, the family of virtually cyclics, subgroups of a group, or so that's the one people know about, finite subgroups, or also just take the trivial subgroup. Always a good family. And then we say, if you take a GCW complex X, is a model for EFG, so the classifying space for the family. If we have the following condition, if we take fixed points, they have to be contractible. So the notation is a bit wonky here. So it's contractible if H is a member of the family and it's empty otherwise. So if you have a family, if your family is just a trivial subgroup, all you're asking for that the action is free and that the space is contractible. Yeah. So if F is 1, then an E1G is just an EG. What's that? That's a universal cover of the KG1. So, and but here, for example, finite dimensional model, you have to the group to be torsion free, but we don't want to restrict ourselves. And why do I write no idea. So, I don't know. Okay, so let me say about maybe 2 minutes, something on some notation would be first. So we talk about the geometric dimension for this family F. That's the minimal dimension of the model for EFG. And if there is no finite dimensional one, then we say it's infinite. And then we say something like G is of type F for the family F. If there's a cocompact model, or F infinity F, if there exists a finite type model, so finitely many orbits in each, or G orbits in each dimension. Or then we have this notion of Fn F. Yeah, so we have up to dimension n. We have finitely many orbits in each dimension. So, and then everybody knows about, well, not everybody, but a lot of people know about E under bar G, which is the same as E thin G. And there are sort of a lot of naturally occurring models, and you just sort of look at spaces you know and groups you know, and then you like think of the most natural space you think of, and usually that's an E under G, and very often it's a cocompact model. So here things are very straightforward. So let's just think of a silly group. I don't know, is it silly? The infinite dihedral group. So we take the real line. That's a model for E under bar G. And well, we have the infinite order element acts by translation, and then we have an element of order 2 which acts by reflection. And we have and every finite order element acts by reflection about something like that. So that's okay. So that's a nice model. So if you think about crystallographic groups.
So wait, if you did the dihedral group and then so it have to be the cyclic things, it would just be a point?
It would just be a point. Yeah, maybe I should say that. If G is in the family, then you always have a point. So it's really not very interesting. For the cyclic group, then the natural model we would think about is Rn, and really it is. Yeah, so again, this is a cocompact model. That one's cocompact. So these are all nice groups, in a way, what you think about. And what else can you think of? Any nice groups? Hyperbolic groups. And then you think about the Ritz complex, as you would, I guess. And that is also a cocompact model. And that's due to Schick and minus group, the other way around. And then mapping class groups. That would be Teichmüller space, I guess. Again, that's a cocompact model, and it's not clear who proved this first, but there's a survey or an article by Mislin explaining why it is. So let me describe scientist Mislin. What else?
Why is it cocompact?
Sorry?
Why is it cocompact?
You can find something. I think it's some kind of retractor. So maybe let's not look at cocompact. But you can find a cocompact model.
Yeah, I guess you can do the usual chop off the cusp or whatever.
Something like that. And again here, outer space or Kohler-Volkmann space is a model, and then you take the spine of it, and that's the spine of outer space is cocompact. And that's due to Prestige and Volkmann. Any other groups I wanted to mention? Oh yeah, soluble groups I wanted to mention. So if you take an elementary amenable group, and then here you really can't just find a space. You have to use a result by look, and a bit more. So you take a group of type F to infinity, so that's the algebraic analog to F infinity, so you have a projective resolution with finitely generated projectives of the trivial ZG module Z. And then they have a cocompact model. That's Martinez-Perez. Okay, and then what you use here, and let me say this, even though, because this is something that is also nice for finite groups, for the family of finite groups, and for the virtually cyclic groups, this breaks down. So this uses some kind of reduction to looking at normalizers of finite subgroups. And so G is of type F in infinity, or F bar infinity. If and only if we have those two conditions, there are finitely many conjugacy classes, finite subgroups. And secondly, we ask that centralizers or normalizers of finite subgroups are of the ordinary type F infinity, or type infinity. Yeah, so you have this thing that you can reduce yourself to looking at ordinary finiteness conditions for centralizers or normalizers, and you just have to look at the finitely many conjugacy class of finite subgroups. The thing is also, if you think about ordinary cohomology, extensions and things work well, but here they don't. Yeah, so if you have an extension of groups and the two groups on the outside satisfy whatever finiteness condition you want to have, the group in the middle doesn't necessarily. So things go wrong, so we have to be careful here. Which in cyclics it gets even worse. So, what do we have? Yeah, so if you have an extension, and even if you take a finite group, yeah.
Do you want to say maximal finite? Or?
No, any finite.
So the normalizer of the identity is the whole group G?
Yes. Yes, your
So,
group has
so one
a-
direction is trivial, is it?
So this direction is more or less trivial, yes. And that direction needs a bit of work. So you really need your group to be of type F infinity. That's necessary.
So that's F
It's
bar
supposed to be a
G.
little superscript F on
Ah,
Yeah.
I mean.
So that's yeah. So I was being lazy.
Sorry.
So this is the same as saying F fin infinity.
Okay.
If I do one underline there.
Okay.
So necessarily we have that the group has to be of type F infinity or F infinity. And yeah, so there are examples here. So where H is torsion free, type F, and G is not of type F infinity for the family of finites. Because, and either of the two conditions can be made to fail. And G has one or two failures. And the dimension also goes up and down, so you have and also the cohomological dimension, G, which is strictly less than cohomological, but now G, which is cyclic geometric dimension here. Yeah, so this and so that's these are old sheet history, and you can even make. Now this gap you can make with G being cocompact, that's due to the Brita and Leary, and you can make Q be a cyclic of order P, that's due to Finiteness. So then it can be as bad as you want it to be. No, not the Brita. What was that? Some subset of the usual suspects, I guess. And so things here are bad, and then if you look at virtually cyclic subgroups, then things get even badder. Is that the word? I guess it's not. So let's say something about, from now on, about virtually cyclic groups. So from now on, F must be sick. And all our notations here, so F is sick, we write F double under bar, one of those things, we write E double under bar. So everything gets 2 bars. Yeah? I think we have to stop at some point. I have a student who looks at this for family of polycyclic groups of Herschel rank 2, 3, 4. And so he doesn't use more bars. But here things are weird, very weird indeed. So yeah, it's very, very difficult to sort of come up with natural examples of spaces for models for these E bar bar G. So of course, if G is virtually cyclic, we have a 1, then we have a point. So there's not much to do. But already if G is free abelian rank 2, it's not so straightforward to construct a model. And the model is not nice. So what do you have to do? So this is, again, so it's because of the Farrell-Jones conjecture. People look at this thing there because it turns up on the left-hand side as you take G covariant homology of this thing that's coefficient in some spectrum. And so this conjecture is the same as the K theory of the group ring. So that's why you're interested in these things. And so Farrell, of the Farrell-Jones conjecture, came up with this example here. So what you do is you have maximal cyclics, so you label them, yeah, so, and we label them by Z. And then we have, of course, G mod HI acts on R xi. So this acts on it, that's an E G mod HI. So that's okay. And then we pull this back to G, and then this xi is a space that fixes HI and is contractible. Yeah. So then we do this for 2 of these things. We look at xi, the join with xi plus 1. And we have 2 things here. And we look at the join. So we get something. Hang on, I can never do this. Something 3-dimensional. Yeah, some sort of weird thing. Weird 3-dimensional thing. And if you look at this one here, that's S3. So there's homology there. Yeah. And then the model for E bar bar G is then we glue all these together. Yeah? So we take the union of these and we glue each copy of xi with itself. Yeah? So if we have a long chain of these things, so we take the union of xi plus 1, where this one here is glue the xi's. Yeah, xi with xi. In xi minus 1 xi. Yeah? So we glue this along and we get a long sort of, what is this? It's not a Toblerone, but it's something. Yeah, it's a long thing. Yeah.
It's close to a Toblerone.
Yeah, so we get this thing. And because of this one here, the third homology doesn't vanish. So this is the smallest dimensional model. Yeah? And the third homology, whatever this is, so this is x, is infinite. Yeah? Infinite dimensional. So really this is the best kind of thing in dimension-wise. And it's certainly not cocompact. Yeah? And X is not cocompact. And there cannot be a cocompact model. I say that in a minute why. Yeah? So already for Z cross Z, the dimension blows up, and we cannot find a cocompact model. And this and something else, another result they had, led Juan-Pineda and Leary how do you put names when one of them is doubled out and then you have a list of names? I never know. So Juan-Pineda and Leary made a conjecture that if G admits a cocompact model for E bar G, then G is virtually cyclic. So the point's the only one. And they had some evidence, for example, so they did it for hyperbolic groups, yeah? They showed this for hyperbolic groups. And if you think back to, look, there you have this nice characterization here, but you don't have anything nice like that. So it's a lot harder to see that a group can have these properties. So let's look at a few things we know. And then let's say what we know. How to construct models. Okay, so so first of all, the reason that hyperbolic groups can't have one of those, and these polycyclic groups or sacrocyclic abelian groups can't have a cocompact model, is that they already fail to have a finitely many orbits of zero self. That's already gone. So that's bad. So here's a lemma. So G is of type F0 with an only F. Yeah, so that's the very easiest thing. There exists a finite set H1. So that the HI virtually cyclics, such that for all virtually cyclics, they have to be subconjugate. Yeah? To one of these elements. Yeah? And this the proof is very easy. It's very straightforward. So well, this direction here is just you take your zero skeleton to be your coset of virtually cyclic. There your transitive G sets of virtually cyclics up to conjugacy. Yeah? Oh yeah, but you know you take our HIs. The HIs we have. So that's straightforward, but the other direction, so you have a finite model, a model that has a finite zero skeleton, so we look at the condition that it's a classifying space, and it says that the fixed points for all these virtually cyclics have to be non-empty. Yeah? And then also the thing has to be contractible, so in particular if you look at the augmented cellular chain complex of this thing, I'm not something sad. But what is this? But if this is non-empty, you can reduce this. If you look, these are permutation modules here, that's virtually cyclic stabilizers, is finitely generated. So we have finitely many summands, and that means for all the stabilizers here, V has to be subconjugate to one of them. Yeah. So the HI are the stabilizers. Of zero cells. Yeah, so, and yeah, because this is non-empty, V has to be subconjugate. One of the HI. Okay, so that's straightforward, and so far all the examples, almost all the examples that satisfy this conjecture, or that don't have cocompact models, already fail this condition here. So let me say a few things. Yeah, so this already failed for hyperbolic groups. Then it fails for elementary immutable groups. Due to Groves and Wilson. John Groves. And then there's a pair of people in Bonn who have just killed off a lot of other examples, a bunch of other examples. So cat zero cube groups acting on cat zero cube group complexes. Acylindrically hyperbolic groups, and what else? Unrelated groups, and they have, I think they have some linear groups as well. And this is from Puttkammer. And Wu. And so they all show that this fails, and actually this led on Puttkammer and Wu to strengthen this condition. To strengthen the conjecture. So they say it fails if any group that is of type F0 for this family the G is F. And finitely presented, because there are examples of groups that up to subconjugacy have finitely many virtually cyclics. Yeah. So there's an example by Higman, just one, I think. Yeah. So there are finitely generated examples, but none of them are finitely presented. There's finitely presented, then G is virtually cyclic. And I have no idea if it's true. Yeah, not claiming. But because, so I kind of think it might not make sense to look, so it's probably true, something like that. So that, or very few groups would admit a cocompact model. So the thing is to maybe look for something weaker, where we basically don't really care what happens in dimension 0. Yeah, so we're saying, okay, we might have infinitely many of those HIs, maximum virtually cyclics, or something of the sort. But we wanted to be as close as cocompact as possible. And because the Farrell-Jones people are interested in homology, colimits come to mind. Yeah? So we look at spaces that are colimits of cocompact spaces. So let's see. What have I done?
Word, too low.
Too low.
The other one. The other word.
Fortunately, I'm reasonably tall. So,
Is this easy to see for Thomson's group, for instance?
Thomson's group F. I would guess there you have infinitely many, so it's difficult to conjugate something. Because if the further you go down in your tree to conjugate into it. But I don't know. For some reason, I think Thomson's group is not F0, but I don't know why I think that. So, so we say G is.
You're just too short.
Is weakly F infinity or F or whatever you want to do is. So what am I asking for? So I'm asking for the family of virtually cyclics to be written as a union of families. Let's have it a countable union. Just be, yeah. And you probably don't need that. And so that for all Fi there exists a finite type, let's say a finite type model for E Fig. Yeah? So in particular, it tells us that any model or there exists a model of E bar G, which is a cocompact model, which is a colimit of cocompact models for smaller families. Yeah? So let's just do away with the F0. Maybe think about Thomson's group. So I mean, it's still quite a strong condition, because one of the things you need to prove, one of the necessary conditions is that normalizers of virtually cyclic groups are, or centralizers of virtually cyclic groups are of type F infinity, ordinary F infinity. Yeah, so G is weakly F infinity implies for all virtually cyclics we have that the normalizer of the this type F infinity. And I don't know, soluble groups are not, in general, of not even weakly F infinity. So that's an old result. So if G is soluble and this condition holds, then and NGV normalizes this at infinity for all the so yeah, so G is to be of type F infinity, so let's have a trivial group here. Then G is polycyclic. Yeah, so it's pretty strong. You would have hoped that, for soluble groups of type F infinity, just without any other condition, you already have a cocompact model for E on the margin here. Things are bad. So what do you do? So basically what you're trying to do is build models for E double under bar G out of models for E bar G. So even though it's not required by the definition there that you have a cocompact E bar G, but let's just assume this. So from now on. Don't really. But hey. Okay, so, and then there's a way of constructing E double bar Gs from E bar Gs by look at Weiermann, and which then reduces it not to look at normalizers, but at commensurators of infinite virtually cyclic subgroups. So let's see what's happening here. So, okay, so we have what do they do? So generally what they do is, and we'll need it for arbitrary, but because we look at these FIs, we don't just look at virtually cyclics and finites, we look at sort of in-betweeny things as well. So we have, what they do is they build, so there are families of subgroups. We already have a model for EFG and they build models for EGG. So what do? They take, so they call I, all this, the set of subgroups that are not in the little group, and they put a strong, what they call a strong equivalence relation on it. So it's an equivalence relation, and what else do we need? We need that if K and H are equivalent, their conjugates are for all G. And if K is a subgroup of something, then K is also equivalent to H. So, and this holds if you look at virtually cyclics or any family of virtually cyclics minus finite ones. What we can take here is H if H is commensurate. So they intersect in something finite index. So we have that they're not finite. Yeah, they're all infinite virtually cyclics. So that's okay. And yeah, and then they define a couple of families. They define family F of V. So V is an I. And they take all the K and I, so K is to V. But now we throw in a little family as well. And they look at the normalizer of the class of V. So this is all the G and G. So in this case, it's a commensurator. So that VG. Here it's a commensurator. Yeah, so having this, you now in place to build a model for E bar bar G. But again, up to conjugacy, there might be infinitely many classes here. So the a priori construction, even in the best case scenario, it doesn't give you anything cocompact. So what you do is you have an EFG here. You have by universal property for these classifying spaces, you have a map from induced space yeah, and then you take all of them. You have a map down here again, because you have a smaller family, because you have all the elements and then your commensurator that lie in F. So you break it up. And then the push out is a model for E bar G. For E bar G or E G G. Yeah, so, and in our case, if we understand those things here, say we have a cocompact model here or finite type model for this space, then there is by some kind of transitivity argument, because any element here is virtually cyclic. Virtually cyclics have cocompact models for the finites. Yeah, that's straightforward. And so you have a cocompact model here. So if you have finitely many classes here, then you're done. And so what we do is we sort of build this slowly up from smaller families of virtually cyclics. Once we can have control of this one here. So we have control of this one, we have a push up of cocompact things. And we're done. So okay, so we have a proposition. If NGV, yeah, so the commensurators have cocompact or finite type models for the bottom left-hand corner. Are not finite, then G is weakly of type at infinity for the virtually cyclic. Yeah. And yeah, and of course it's not always easy to compute those commensurators here. So what you can do is there's a condition that read more or less is about so suppose for all there exists a cyclic or even a virtually cyclic, there exists a C commensurate to B such that C is normal in the commensurator, or in its normalizer. Yeah. So let's say we have this condition, then we reduce to looking at normalizers, already better. But we still have this family here. Yeah? So we basically what we do here, we join everything, all V and all its subgroups that are commensurate and conjugate and so on to it, if we then extend it to G. Yeah, so that's what we do here. So we have to still get control over this class here, which is a family, which is still not so straightforward. But for what you could do is just factor it out if it works. Yeah, so for G polycyclic, the way you read Luke-Weiermann carefully, their construction. Maybe I should say something about how you prove that. You just adjoin one after the other, and you make sure you use using that push-up down there. And you make sure that if you adjoin one family, and so on, at some point you end up having so you extend f of v, taking all the conjugates of everything that's in there in G, not just in the normalizer. You construct one of a space for those, for G, not just for the commensurator, and then you adjoin the next one, the next one. So for G polycyclic, what Luke-Weiermann do, they compute the dimension, but if you read what they do, then it works for virtually f infinity, weakly f infinity as well. So, of course, if you take NGC mod C, then this has a cocompact model for E bar. And you lift this back to NGC, and you get your cocompact model for this family f of C. So that's okay. So they are of types weakly f infinity. And hyperbolic groups, but this was already basically this is clear from what Juan-Pineda and Leary did. Every virtually cyclic is contained in the maximum virtually cyclic, which is the normalizer. So that's okay. They're also of type. And so that's due to Juan-Pineda and Leary. And then we try to do is lovely class course. A lot of people here who know a lot more than I. Mapping class groups. So theorem, yeah, I think it's a theorem. Okay, they even have type F without the infinity. Yeah. Okay, so, and this is down to carefully reading a paper by Untitled Chapter. And so they show that they satisfy condition star. Okay, maybe I should say first. So what you have to look at is of virtually cyclics that are not finite. Let's wipe a few things under the carpet and let's just look at cyclics. So we look at elements here. And they, if they're pseudo-Anosov, there's nothing to show. Because there's a McCarthy. Not McCarthy. Yes, McCarthy. And the normalizer is virtually cyclic, so there's nothing to prove. So really, we just need to look at cyclics generated by reducible elements. And so they satisfy star, so we need to look at normalizers of reducible elements. And we look at the cutting, that famous cutting homomorphism, where we look at the mapping class group onto fixed points as stabilizers of the curve complex to mapping class groups of smaller, of sort of cut up bits of mapping class groups, and the kernel is virtually cyclic. The normalizer would be finite index in there. And so you play around with the normalizer and look carefully at what happens with this map. The kernel might be virtually free abelian. So, and as I said earlier, finite index things mess things up, so you have to be careful and look around. But in the end, it turns out that you have your normalizer setting here, and it maps onto something that we have control of, which is a Riesz product of normalized of smaller things, and the kernel is also extremely bad. But I don't want to go there now. So yeah, so we have mapping class groups, and let's see if we get some other groups as well. Thank you. Are there any questions?
Do you think there's hope for doing this for hierarchically hyperbolic groups? I don't think any of the hierarchically hyperbolic Borg are in the audience, but I'm sure one of them's around. There's normally one of them.
Okay. Yeah, so I don't know about them. So. But yeah, I'm sure that, I mean, these normalizers or commensurators are probably, they're quite a class. There are probably a few classes where you can actually understand what's going on.
I mean, the most troubling thing seems to be what you said about passing to finite, and if it's quite delicate,
Yeah.
other passing to finite.
Yeah. That usually is the problem. Yeah, in this family here, even though it is, so you don't have your finite subgroups, you allow some bits to become contractible. So there's a student of Thomas Weigel, what's his name? Federico Passini. He computed these things for braid groups. Yeah.
The very groups.
No, not for braid groups, yeah. For some braid groups, but only for certain elements, and gets cocompact methods for these things here. So there he can control the commensurate. More questions? Then let's thank Brita again.